properties of matter in the last, and now we should be set to start simple harmonic motion soon. Anyhow, so let's begin. So we have not discussed viscosity yet, right? We have only discussed till surface tension. Is that correct, people? Or have we discussed viscosity also? Viscosity is done. Okay. So then we have to discuss the doubts today. Okay. So firstly, if you have any doubts from HC Verma, please send it to me on the text message or let me know. Properties of matter, right, Kshitij?
Yes.
Okay. Okay. So let's begin with this. So HC Verma, properties of matter, question number 12. Let's begin with this one. Just go through the question, everybody. We'll discuss. Okay, so let me start by explaining the question. Right, so says that copper wire of given cross-sectional area and tension is this much. The decrease in cross-sectional area of the wire, Young's modulus and Poisson's ratio is given to you. Okay, so you have to just use that concept. So the given information in the question is the tension that is given to us as 20 newtons. Okay. The cross-sectional area that is given to us as 0.01 centimeters square. Extremely thin wire, as you can see. And Young's modulus is given and Poisson's ratio is given. So Young's modulus for copper is given as 1.1 into 10 raised power minus, 10 raised power 11 and Poisson's ratio gives us a 0.32. So the first thing is, from this we will see that the longitudinal or the tensile stress is equal to this quantity. So it is 20 divided by 0.01 into 10 raised power minus 4 in Newton per meter square. So it's becoming 2 into 10 raised power 7 Newton per meter square. So that is our tensile stress. So from that we will know, using Young's modulus is equal to tensile stress upon tensile strain. We'll know that delta L by L is equal to stress upon Young's modulus. So it's around like that. Actually, when you approximate it, it will become 1.9. So this is our longitudinal strain. Now Poisson's ratio. So how will we use the value of Poisson's ratio here? Poisson's ratio is the ratio of the fractional change in diameter of a circular object, or rather cylindrical object, with respect to the longitudinal strain, or delta L by L. Okay, so using that definition of Poisson's ratio, we will calculate the fractional change in diameter, and from that we will calculate the fractional change in area using the concept of propagation of errors. So hope it is clear up to this point, friends. So Poisson's ratio is the modulus of fractional change in, so that's how the minus sign comes in, where d is the diameter. So from this you can see that the fractional change in the diameter will be negative of Poisson's ratio, which is 0.32 multiplied by the fractional change in length. This much.
Sir.
Yes.
Sir, what is Poisson ratio?
Poisson's ratio is this thing. It is the fractional change in diameter divided by the fractional change in length. So when you have material whose natural length is L and natural diameter is D, but because of stress, you subject it to a elongation like this, then the diameter will tend to decrease, because you have created stress by applying external force. So the Poisson's ratio is the material property, which you know is defined as the ratio of negative of the ratio, because the diameter will decrease when the length increases, and vice versa. So delta D by D divided by delta L by L. So the quantity in that inside the bracket will be a negative quantity, because if the length expands, then the diameter will decrease, and vice versa. So the added minus sign is to make Poisson's ratio a positive quantity, a modulus quantity. So is it clear now? So this is a fractional change in diameter. Now diameter is twice of radius. So since diameter is proportional to radius, that means the fractional change in diameter is equal to the fractional change in radius. Whereas area, so from this now we know that the fractional change in radius is also the same thing. And area is equal to pi r square. So since area is proportional to radius square, so the fractional change in area will be 2 times the fractional change in radius. Or that's the same thing as 2 times the fractional change in diameter. So our final answer, the fractional change in area will become minus of 2 into 0.32 to 1.9. So just make sure you note down the concept and the application of the formula in solving this question. All these questions are formula based. There's nothing difficult about them. Now we'll move on to question number 10, which number of people have asked, including Tej. 10 and 11 also we will do next. Okay. Shweta and Tej have both asked question number 10. So we will do these following questions now. We will do ten, 11, 12 we've already done, and there is somebody who's asked for 20. 13 also. Okay. Twenty-two, 29. 32. Also question number 14. Okay. Anyhow, so let's start with 10th and 11th next. Just go through the questions, I'll explain. Okay, so let's understand question number 10. Hope all of you have gone through it by now. So again, it's that type of question where all the data is given to us. So sphere of given mass is suspended by a vertical wire whose natural length is given and diameter is given. Now, when it is in equilibrium, there is a clear gap of 2 millimeters between the sphere and the floor. Whereas when the sphere is gently pushed aside so that the wire makes theta with the vertical and all that, the maximum value of theta so that the sphere does not rub the floor, Young's modulus is given to you. You need to make approximations appropriately. So to understand that when you release the sphere from that given position, so it is swinging like a pendulum. So now when it comes to the vertical position, the tension in the wire will not be the weight anymore. It will be because along with mg, there will also be centrifugal force acting on the sphere. Okay. So if you just leave the sphere at rest in the vertical position, then it's a different situation. It's not going to have any centrifugal force acting on it. So at that point of time, if you look at the tension in this wire, okay, that will be just equal to mg. So if this is at rest over here, then the tension in this situation, let's say T naught, this T naught is equal to mg. So if its length has stretched to L plus delta L, if its area of cross section is A, Young's modulus is Y and all that. So you can see that T naught divided by A, that is stress upon strain, is equal to Young's modulus. So delta L is mg upon Ay into the natural length. Now in this situation, what is happening is that it's given to us that there's a gap between the floor and the sphere. So it's given to us in the question that natural length is this much, diameter so much, all right. There's a 2 millimeter gap between this and this. Okay. So this gap here, let's say D, that gap is 2 millimeters. Okay. Now what we do is, next up, we take this to a position like this, okay, and we release it from here. So now by the time it will become vertical, what will happen is that the sphere has already got some linear velocity. So from this position theta, if we release it, by the time it's come here, it's got some speed, it's in circular motion. So the tension will be different now. Okay. And we want the situation that it should not hit the floor. So now the new value of the tension that is there, that is going to be equal to, so it should just about clear the floor. We want that situation. Okay. So this T will become mg plus mv square by whatever this R is. So the R over here is like delta, you can say L plus delta L prime, because now the extension is going to be different compared to the previous case. Why? Because there's more tension, so there's going to be more extension also. So from this point of suspension, this length is going to be different from what it was in that previous case. It's going to be a little bit more. So this delta L prime should be less than equal to delta L plus D. So when delta L prime is equal to delta L plus D, is just about hitting the floor, just about touches the floor, that condition. Okay. So we have this equation, okay, and we have this equation. So now T upon A divided by delta L prime by L is equal to Young's modulus. So the new value of the extension is going to become mg plus mv square by R into L upon AY. This is basically the next one. So now in this we have to put the condition, this condition we have to put, that if delta L prime is delta L plus D, it's just about touching. Okay. So compare equation 1 and 2. That gap. For that limiting condition we have that's your delta L prime, that should be equal to delta L, which was mg into L upon AY plus D. You can see this term and this term will cancel. So we have the relation that mv square by R into L upon A into Young's modulus should be equal to D. So this is the equation we have to solve now. Now in this we'll also use work energy. Now from conservation of energy, you can see that as this bob is going from this position to this position, if the height difference is h, half mv square, which is the speed at this position, is equal to mgh. So v square is equal to 2gh, where remember from circular motion, this h is this kind of term. So further we have this relation that m into 2gl into 1 minus cos theta, and in the denominator also r we will equate more or less to l, because r is slightly greater than l but not such a significant difference. Okay, so we'll take r as approximately equal to l. So that's mv square by r, this whole term, into l upon ay should be equal to this. So you can see we'll get 2 mg, right, upon ay into 1 minus cos theta into l is equal to d. Now we'll start substituting the values. Okay. So 2 times the weight of the object, which is given to us as 20 kg. So I'll take the weight as 200 newtons divided by the area. So for that, diameter is given to us as 1 millimeter. How much is it? 1 millimeter. So the area will become pi into 0.5 millimeters. So that's this much square. Okay. Into Young's modulus, which is given to us as 2 into 10 raised power 11. So that's this term. This whole term into 1 minus cos theta should be equal to small d, that is the gap between the floor and the sphere in the equilibrium position, which is given to us as 2 millimeters. So this equation now we have to solve for theta. So when we do this calculation, we'll see that we'll get 1 minus cos theta to be, I think, a reasonably small quantity. So we can do approximation. See that this will become pi into 0.25 into 2, so that will be 0.5. So I write that as 5 into 10 raised power minus 7 हो जाएगा plus 11. So that is 4 divided by 400 from this. Okay. So we'll get 1 minus cos theta as quite a small quantity. So if 1 minus cos theta is a quantity which is small compared to 1, you get 1 minus cos theta as pretty small compared to 1. That means cos theta is quite close to 1. That means theta is a small angle. So for small theta, we can use the approximation that 1 minus cos theta is how much? It's approximately theta square by 2. Because we have that series now, cos theta can be written as 1 minus theta square upon factorial 2 plus theta to the power 4 upon factorial 4 minus theta to the power 6 upon factorial 6, this series method. So for small theta, we can always approximate cos theta as 1 minus theta square by 2. So small angle approximation. So this side will just become theta square by 2. That is approximately equal to this value, which you can see is actually pi by 4 into what is it, minus 3 plus 4, it's 1, it's 1, 2 divided by 2. Something like this you'll get. So theta square is approximately equal to pi by 2. So from that theta you can calculate how much it is in radians. Just check my calculation part once, but this is a more important thing, this expression. Now in this expression, you are substituting everything. And finally, 1 minus cos theta, I'm approximating as theta square by 2. That is what they meant in the question by saying that use appropriate approximations. It is given as a hint in the question. So I'm just scrolling up first, so you can take down this part about the mechanics application, free body diagram and all that. So go through this section first. Okay, so I'll just scroll down now. You can see the comparison of equation 1 and 2 on this page that I've done. Okay. And from that only we solve for that term. Initially we solve it for 1 minus cos theta, and then we approximate the value of 1 minus cos theta as theta square by 2. Okay, so I think we'll just check the calculation once more. So the weight was this much, area was pi r square, so that was okay. So let's just check this part of the calculation. So I've substituted mg correctly, I've substituted area correctly, Young's modulus correctly. On the other side, d is correctly substituted, so I should get 400 upon pi into 0.25 into 2 will give me 0.5. Okay. So 0.5 into 10 raised power minus 6 plus 11, so that is 10 raised power 5 into 1 minus cos theta should be on the other side, 2 into 10 raised power minus 3. So 1 minus cos theta should become into 5 pi into 10 raised power 2 from here divided by 4. Yeah, so I think the calculation is correct up to this point. Sorry. Okay, so when you convert this to degrees, when you convert radians to degrees, you will get the answer. X radians is equal to x by pi into 180 degrees. So here 1.23 radians will be equal to or actually we don't need to use the approximation because actually the value is not too small. So instead of using the approximation, what we'll do is we'll do the calculation from here now. So this pi by 4 is approximately how much? It is 3.14 divided by 4. So that's nearly 0.8, little less, 0.78, let's say. So that means cos theta is how much? It is 1 minus 0.78. So it's 0.22. So theta is cos inverse 0.22. Now from this you can look up the value of theta in a table or using a scientific calculator, and you can work it out. Okay, so you'll get the answer as per that. So let's move on to question number 11. No, there was the 400 in the numerator, no? But that's why it got 10 raised power 2. This 0.5 into 10 raised power 5. But there's also 400 in the numerator here. So I made it. Okay. Now let's move on to question number 11. Okay, so we have a steel wire which is clamped at both the ends. So it lies horizontally when it's without any tension. But when you attach a load at the middle point, the wire gets depressed and it sort of makes a kind of Y shape. So the calculation is based on that concept. Let's say this is our steel wire, which is clamped at both the ends and it remains horizontal when we are not putting any load on it. So at that point of time, there's no tension. So it's at its natural length. So that natural length is given to us as 1 meter. Okay. And this is steel wire. So Young's modulus of steel is given to us. It is 2 into 10 raised by 11. The cross-sectional area is given to us as 4 millimeters square. Now, next what we are doing is we are going to attach a load to the midpoint. We are going to suspend the load from the midpoint. As a result of that suspension, let's say the shape will become like this. So it might not get so much influenced by it, but I'm just making a exaggerated diagram. So the wire will do what we call, it will sag because of this load attached. So this mass that we've attached is now 2.16 kg. So as a result of that, to find the vertical depression or the amount by which the wire is sagged. So this distance here, this is the distance by which it is sagged. This D we have to calculate. With L by 2. So what is happening now is that the wire has got extended. So this part has become L by 2 plus delta L. This has become L by 2 plus delta L. And as a result of that, there is a tension which is acting like this. So if you look at the free body diagram, there are these two tensions, which you can see are acting at symmetrical angles theta with respect to the horizontal. So this angle theta below the weight of this object is acting at that point equal to mg. So one is we have the relation that 2t sine theta is equal to mg. So the tension that is developed in the wire is mg by 2 sine theta. And as a result of that, the stress developed in it is this much. And as a result of that, the strain developed is equal to stress divided by Young's modulus. That is this much. Now in the diagram, you can see that sine theta is equal to d upon okay. And from that only we'll do this calculation. From this, we need to calculate the value of d now. Okay. So we need to do a bit of approximation here. Now what we'll observe is that theta will be a small angle because that sag d will be very small compared to L. So we can approximate sine theta as basically d divided by L by 2. Okay. And so we'll apply that approximation over here, and that's how we'll calculate the value of d. So just note it down up to here, then we'll put the numerical values and do the calculation. Okay, now one more simple thing that we can do here. So see, when we use this approximation, instead of substituting sine theta as this complicated thing, we're substituting sine theta as just 2d by L. So this becomes like this, that this equation, after using the approximation, it becomes delta L by L is equal to mg upon 2ay into d divided by L by 2. So this side becomes simple. Okay. Now to make the left hand side equally simple, now what we can do is we can use Pythagoras theorem. So L by 2 plus delta L is basically equal to how much it is? L by 2 whole square plus d squares square root. So there is just one thing here. There will be a factor of 2 here because I have taken delta L to be the the hypotenuse. No? L by 2 plus delta L is the hypotenuse. So the total length of the wire has become L plus 2 delta L. So this will be, or basically I should take this by 2. That will be the easier way to understand it. The wire has stretched from its natural length to L plus delta L. Okay. So the hypotenuse in each case is actually half of this. Now it is L plus delta L whole thing by 2. So it's easier if we do that. Okay. So everywhere here, substitute this as L plus delta L whole thing by 2. So anyhow, more or less doesn't make a huge difference here. Now because this is a small angle, because D is small compared to L, so we are doing this approximation. So this fine. Yeah, the total wire has stretched in length from L to L plus delta L. So each hypotenuse in the two triangles is half of that total length. So it's L plus delta L by 2. Okay. Now in this, you are substituting the sine theta term from here as this. Okay. So substitute this here. So we have delta L by L is mg upon 2ay, and sine theta is 2d by L. So that is mgl upon 4 times a by d. Now comes the binomial approximation part. So in the binomial approximation part, I will use this, that this thing, that L plus delta L whole divided by 2. That hypotenuse is this much. So what I can do is I can take L by 2 common. So this will become 1 plus delta L by L. And from here also I can take L by 2 common. So this will become 1 plus 2d by L whole square to the power half. So this is where we'll apply binomial approximation now. So this can be approximated as 1 plus half into the power comes inside binomial approximation. 1 plus x to the power n is approximated as 1 plus nx if x is very small compared to 1. So here you can see that 2d by L whole square is very small compared to 1. So that way now you can see that cancelling of the L by 2's and then the 1, I can say delta L by L is equal to how much? It is 2d square by L square. So this is the other approximation. So one is I'm approximating sine theta from small angle approximation. So it's becoming this. And the other is I'm using binomial approximation to get this. So this equation now, this equation that we had started out with, that I have delta L by L also and sine theta also. Now delta L by L's approximate value is becoming 2 times d square by L square. Now on the other side, sine theta's approximate value is becoming 2d by L. So from this, I can now calculate the value of B easily. Okay, so people, that was question number 11. Now let's move on. I think we're doing question 13 next, right? Yeah. 10, 11, 12 is done. Let's move on to 13 and 14. Okay, so just go through question 13, all of you first. We'll discuss. So it's a direct question. We want to find the increase in pressure required to reduce the volume of a water sample by a given percentage. So that means that you want the volume change by a factor, you want to reduce it. So delta V by V will be a negative quantity because the volume is decreasing by a factor of 0.01%. That means delta V by V will be how much? It will be minus of 1 into 10 raised by minus 4. Now you apply the concept that volume stress upon volume strain mod is equal to Bulk's modulus, or delta P divided by mod of delta V by V is equal to Bulk's modulus. So delta P divided by 1 into 10 raised by minus 4 is the Bulk's modulus, which is given to us to be what it is, 2 into 10 raised 2.1 into 10 raised by 9. So the change in pressure that is required is the product of this. So 2.1 into 10 raised per 5 pascals, or 2.1 atmospheres almost. Okay, so hope this question is clear. So moving on to 14th question. Just go through 14th question. So there you have to apply the concept that at a certain depth underwater, the excess pressure is the hydrostatic pressure rho gh. So it's like a reverse of this question. There you know the excess pressure. From that you calculate the volume strain. And once you know the volume strain, that from that you can calculate the percentage change in density. Okay, so just try out question 14 yourself. We'll discuss. Okay, so let's go ahead with the 14th question. So the change in density of water in an ocean at a depth of 400 meters below the sea level. So the excess pressure at that depth will be rho gh. So that is, you can take the density of water at the surface only, 1030 kg per meter cube, into g is not given to us, so we should take it as 9.8 into the depth of 400 meters. So this is the excess pressure in pascals. So now excess pressure divided by delta V by V, this has this much. Okay, so the volume compression, when you remove the mod, it will be minus of the excess pressure divided by the bulk's modulus. So minus of this value, so I'll take this for the moment as this much only, divided by bulk's modulus of water, which is seawater, which is given to us as 2 into 10 raised per 9. So this is giving us the volume strain. Okay. Now density is equal to mass upon volume. No? So density is inversely proportional to volume. So fractional change in density or percentage change in density is negative of fractional change in volume. So if the volume decreases, the density will increase by a factor. Just need to substitute this here. Okay. So because the volume is decreasing, the density will increase. So our delta rho by rho is coming out as a positive quantity, and this is what we needed to calculate. Now actually we have to calculate the change in density itself. So the change in density you just cross multiply. No? Delta rho by rho will be equal to this fractional change into rho. So it's this is the fractional change and multiplied with the actual density. So this will be the change in density. So that this much in kg per meter. Okay, so that's question number 14. So just go through the solution of this carefully once. Just a minute, I'll just reference the question. So next we move on to question number 20. So let's take this down if required and then go through question number 20 next. 20 and 22 we'll discuss these two. Okay, so hope all of you gone through the 20th question. Let's discuss it. So lower end of a capillary is immersed in mercury. So the level of mercury actually goes down. The level of mercury is found to be 2 centimeters below the outer level. If the same tube is immersed in water, up to what level it will go up. Okay. So first of all, remember the difference in contact angle between mercury and glass versus versus water and glass. If you have a water surface against a glass wall, the water meniscus or the contact is like this. This is the situation with water, where the contact angle is between water and glass, the contact angle is actually almost tending to zero. So why this is not given in the question is because in HC Verma there's a table of values of contact angle. So you're supposed to use that for solving this type of a question. Whereas when you have a mercury surface in contact with glass, the contact angle is an obtuse angle and it is nearly 135 degrees. Mercury glass interface. Okay. So this is the concept we have to use in this question now. So in one case, if we are inserting a narrow capillary into a surface of water, and in the other case, we are inserting the same capillary into the surface of mercury, you'll see that the water level will rise because of the acute contact angle and a positive pressure difference it will create. Whereas the mercury level will in fact decrease. So this capillary is in water. You'll observe is this kind of situation. It's in water. And this height of so here for water glass, the contact angle will substitute nearly as zero. T will be surface tension of water. And rho is density of water. It is the same thing if we insert this in mercury. What we'll observe is that the mercury level actually goes down inside because the meniscus is the other way. Meniscus is a outward bulge like this. So this depth is actually equal to minus of h, which is for mercury glass. Okay, so we'll have this thing that 2 centimeters is equal to 2 times surface tension of mercury into 1 by root 2 divided by 13.6 into R into G. Whereas for this one, we have the unknown height is 2 times surface tension of water into 1, because cos theta will become 1, divided by density of water, which is 1 gram per cc into R into G. So comparing these two equations, you can see that H divided by 2 centimeters is going to be equal to the ratio of the surface tension of water to surface tension of mercury into root. So just look up the values of surface tension of water and mercury from the table given in HCFM. Substitute that here and you'll get the answer. Okay, so this was question number 20. Now next we are moving on to 21. Sorry, to 22. So in question 22 also, you assume that the capillary is made of glass and the contact angle between water and glass is 0 degrees almost. Okay. Try it out with that information now. Okay, so let's look at question number 22, people. So again, the same situation. Narrow capillary in water. So here also the water will slightly curve at the point of contact. Anyhow, so let's assume this is our capillary action. Water, this is a glass capillary. So the radius of the glass capillary is given to us to be 0.5 mm, and surface tension of water is given to us to be 0.075 Newton per meter rather. Okay, and contact angle, we'll take the standard value. So this capillary height, first let's calculate that. So H is equal to density of water will take as 1000 kg per meter cube. Sea water is slightly less because of slightly more because of dissolved salts, but here we'll assume pure water. So 2 into 0.075 into cos 0, which is 1, divided by 1000 into 0.5 into 10 raised per minus 3, right, into G, which I'll take as 10. So what we're getting here, we're getting 150 into 10 raised power minus 3 in the numerator, divided by 5 into 10 raised power 0 in the denominator. 30 into 10 raised power minus 3, or 3 centimeters, right? That's the capillary height that we are getting. So find the difference between the pressure of water in the tube 5 centimeter below the surface and the atmospheric pressure. So now such a point which is 5 centimeters below the surface inside the tube will be here. So this depth from the surface is 5 centimeters. So what will be the pressure at this point? For that we have to compare this point with this point on the surface. So it is 2 centimeters below the point on the surface, because H is 3 centimeters. So this difference is, so pressure at that point P will become atmospheric pressure plus rho G into 2 centimeters. So the pressure difference between that point and atmospheric pressure will be this much. So 200 pascals. So this is question number 22. So the only thing you have to understand is that if the contact angle is not given to us, we have to use it as the standard value for glass and water from the table given in the chapter. In JEE exam, it will be given to you, but here. The answer is given as 190 instead of 200 because they've taken the value of G as 9.8. I've taken the value of G as 10 this year. Okay, so just complete this and then we'll move on to question 29. Next. Okay, so let's move on to question number. Just a second. Okay, so let's go through the question number 29 again. So what is happening in this is you take a wire frame and you created a film of soap solution in it. So let's say this is your overall wire frame and you dipped it inside soap solution and brought it out. So there's a film of soap. So this is a soap film. Now next what you do is you place a piece of thread, a thread loop, and then you plug the thread loop in its center so that there's an air gap. So this thread loop, this part inside it is an air gap, whereas it is surrounded on other sides by the soap film. So the soap film will be applying force due to surface tension like this, and that force will generate tension. Okay. So now if you consider a free body diagram of that, so this is a diagram of that thread loop. And there is soap film all around it, like this. So force due to surface tension is acting like this. So it's getting pulled outwards because of that. This is so if you consider a sectional length DL like this, you'll experience a force due to surface tension that is equal to how much? It is surface tension into dA, because that is how surface tension is defined. No? It is tangential force per unit length. So now next thing what we'll do is we'll make a free body diagram of that small section of length dA. FBD of a section dl of the circular ring. Okay, the thread loop basically. So imagine a magnified diagram of that sectional length dl. So if it is subtending at the center of the circular loop, so this is the whole circular thing. subtending an angle d theta. This is the radius of the loop. Then it will be experiencing tension here and here tangentially like this. And it will be experiencing force due to surface tension like this, radially outwards. So if you see this line, it bisects this angle. So this angle is equal to this angle, d theta by 2, and that will be the same as this angle here, d theta by 2, because this angle is 90 and all that like that. Okay. So this angle is 90 here and tension is acting tangentially. So this angle is 90. From that angle is d theta by 2. So now you can see this angle is also d theta by 2. So the component of tension towards the center, that is 2t sine d theta by 2, has to balance the force due to surface tension outwards. Okay. So that is 2t sine d theta by 2 has to balance surface tension multiplied by dl. Now dl is r d theta, and sine d theta by 2 will approximate as d theta by 2, small angle approximation. So using that, the left hand side becomes this much, the right hand side becomes this much, and you can see that now I'm confusing surface tension with tension. So what I'll do is I'll write a different symbol for surface tension. We'll use the symbol capital S for surface tension. So going back here, change the symbol. So S is the surface tension of the solution, whereas T is tension in the wire. So over here T is the tension in the, not the wire, rather the thread, the tension developed in that. Right, so we can see that T becomes S into R. Only there will be a factor of 2 over here. I'll tell you why there will be a factor of 2, because there are two surfaces which are in contact, the upper surface and the lower surface. So this 2 is there because there are the net force on the element dl comes from two surfaces that bound the film. Okay, like we've done in derivation of surface energy also, we've seen that a thin film of solution has two surfaces, one upper surface and one lower surface. So accordingly, so that is question number 29. So we will conclude here today with this. Okay, we have one more lecture this week. So in case any more doubts are pending, you can conclude that then, and we will start with simple harmonic motion in the next lecture. So that's it for today's session, people. Wish you all the best and thanks for attending. Bye.